Good morning. So, we will continue on our class on analog electronics. Today is lecture 2 and let us just quickly recap what we have covered so far. So, we have covered the signal chain of the amplifiers, we discussed about the voltage and current sources and their internal resistances. We discussed about frequency spectrum, Fourier series of periodic and aperiodic signals. We discussed about the analog and digital signals, how to convert a analog signal into corresponding discrete components, about the ADC and its binary component, and then we discussed about amplifier, right. So, I believe up to this it was discussed. Now, this efficiency of power, efficiency of amplifier also has been discussed. That is, we have to calculate the total DC power and we have to calculate the load power, and the efficiency is load power by the supplied power. This is the transfer characteristics of amplifier and it shows the linear region and the saturation region. Symbol convention for instantaneous current, total current and AC current, right. So, if we want to represent any AC or DC component or total component, we should use these notations, right. So, we were up to this. So, as I said that in a voltage amplifier, what is our requirement? Input impedance should be, can you recall, what is a, if I have a voltage source, what is the source resistance supposed to be? Ideally should be 0, right. Similarly, if you have an input, so this model, this is a 2-port network, right, or you can say circuit model, equivalent circuit model of an amplifier, this is a voltage amplifier, okay. So, this model, this is actually replica, or you can say I am mathematically modeling any amplifier which is looking like this, and you have studied op amp, right. What is the symbol of an op amp? This is the symbol, right. So, this thing we are modeling like this, okay, but this is also a symbol, right. Inside actually you are having some circuits, right, amplifier circuit we are representing, so that always if you draw a big circuit then it is difficult, right. So, this is a easy representation, this is just an representation. So, this is a symbol representation and this is a model, circuit model or mathematical model representation. So, how we are representing? This is my input port, right, this is, it is interactive with input, and this is my output port. Input port, what we are having? We will be seeing some resistance here, right. So, that is modeled by Ri. Output side we will be having some resistance, that is modeled by Ro, and this will be having some gain of say V0, that is modeled by this dependent voltage source, that is it, okay. So, do not get confused by this diagram, this is just the mathematical model. What is the job of an amplifier? Job of an amplifier to give you a amplified voltage signal, right. Suppose this voltage source is Vi, differential voltage. So, this V0 will be amplified version of this Vi. So, that is it. So, it is doing the same thing, clear. So, this Vi is nothing but this conversion, right, this Rs by Ri, those terms will be there, okay. So, do not get confused by this model, this is actually an voltage amplifier, 2-port network of an voltage amplifier. So, we can calculate easily by this by the using the what? KVL, okay. Using KVL we can easily calculate this. and we can find out what is the voltage gain, output by input. Now, how many type of amplifier could be there? This is a multi-stage amplifier, where we discussed that several stages, 3 stages here are connected in series, right. So, it will be just like this. Now, can you tell me what is our RI requirement? Input impedance of an voltage amplifier should be infinity, very large. What is our output impedance requirement? Very less. So, in between we should have a high gain. Okay. So, this amplifier should be selected so that this one is giving me high input impedance, this one is giving me low input impedance, and in between we will be having high gain A1 into A2 into A3, that should be our total overall gain, right. So, if you see this amplifier how they are connected, the first one you see its input impedance is 1 meg. So, this is satisfying our first criteria. Output impedance 10 ohm, satisfying our output criteria. In between we are having gain of 10, 100. So, total 1000 already achieved. So, last stage you see our gain requirement is not important. What is important? Output impedance should be low. Okay. So, these are arranged by such a way. Now, there are other amplifier topologies also. We already discussed voltage amplifier. Next is current amplifier. So, for current amplifier we will be having a current source, right. Okay. And ideally this current source impedance is very high, right, infinity. So, if I want to talk about the current gain, this internal circuit is having a current of II and output current I0. So, this is my internal short circuit current gain. Okay. If we short this, only this current will flow I0 by II, but if we want to see the overall current, then what we will do? We will add a resistance here, load resistance RL, and then we will cover I0 by IS. This is overall current gain, right. So, this II is my internal, I am not considering the source current. So, can you tell me what should be my input impedance RI and what should be my output impedance requirement? RI should be very less and RO should be very high. So, that why? Because our now job is to deliver this current to the load. So, if this is high, so no current will flow through this, all current will flow through the load irrespective of the load resistance. So, it is just opposite to the voltage amplifier. So, always remember that current amplifier and voltage amplifier like a conjugate, right. So, opposite, the input impedance output impedance requirement is just opposite. Apart from input and current and voltage amplifier, how many others amplifier can be? So, if you see this, input side is current, output side is also current. So, both side are current, it is a current amplifier, both side are voltage, it is a voltage amplifier. And how others can be? I into V and V to I, right. So, V to I is V by I is equal to resistance and opposite transconductance. So, we will be having one transconductance amplifier and one transresistance amplifier. Okay. So, these two already you know, both input side and output side same voltage and current, and their requirement also you know. So, now you can calculate what should be for other two composition. What you have to just think that what is my input side, is it current? Then you think that okay, for if it is input side is current, what is my input impedance, should be 0. So, you see this trans resistance, output is voltage, input is current. So, input impedance should be 0. Now, voltage you go, output voltage, output impedance should be 0. So, both you combine, you get 0 0 for trans resistance. Trans conductance, input side is V, input side V, input impedance requirement is infinity. So, it is infinity. Output side is I, current amplifier, output impedance is infinity. So, this is also infinity. Okay. So, by combining these methodologies, if anyone asks you that what should be input impedance requirement, what should be output impedance requirement of this particular amplifier, you will be able to answer. Okay. And just how you should think that what is your objective. Your objective is to whatever the voltage source or current source to transfer totally to that, then what should be your resistance requirement. Okay. And if it is a voltage source, your source resistance in series, if it is a current, it is a parallel. If you remember these two things, rest of the stuffs you can automatically calculate or arrive. So, you do not need to remember this, you analyze this. Okay. I will not tell you that okay, you just remember these configurations. I will request you to remember how to analyze that, then you do not need to remember this, you will readily, it will be, you can recall this. Now, if I tell you how to find a input and output impedance, okay, you have an amplifier. So, I have an amplifier. So, how could I find the input impedance? What we will do? We will add a voltage source at the input side, we will try to find the current, and we will now divide Vx by Ix, we will get R in. And generally input side you have seen the two port network, input side and output side, there is a no direct connection. So, you can directly use this. You can keep this output load open, or you can make it short circuit or open circuit, that is okay. So, what is the rule saying? That input resistance Ri of the amplifier can be determined by applying an input voltage Vi and measuring the input current Ii. So, if you divide them, you will get the input impedance. Now, to do the output impedance, what you need to do? Now, see, in the output there is a dependent source. If you see the two port network, this source depend on this voltage, right. So, to find the effective resistance, you have to first make this 0, this effect you should make this 0, right. So, that this output source is not modified by this voltage source, right. It was not in the case of previous, because previous only Ri was there, right. So, what we can do? We can sort this voltage. So, this is 0. So, this will also come as 0. So, as if this effect is not there. Okay. So, what is written, you see, the output resistance found as the ratio of the open circuit output voltage of the short circuit output current. Open circuit output voltage to the short circuit output current. So, what we are actually doing, that input side, if there any voltage source, we will make them short, so that their effect is not coming, and if it is a current source, we have to make it open. Okay. This will break, so no current will flow. Okay. But if it is a voltage source, it is in series, so you have to make it short. Means I have a voltage source, I will add another wire to short it. okay, so that this voltage effectively now 0. But if it is a current source, as this is a parallel connection, what we have to do? We have to make this open. So, if it is a current amplifier, you make it open, so that ultimate what is our aim? This side no effect should come, only what we are interested about this, not about this. Okay. So, that is it, that is the thing. Okay. So, if any amplifier is given, if I ask you what is the input impedance, find a input impedance, what you will do? You will find a what is my input voltage, and you will find a what is my input current, and you divide them, you will get it. Output same thing, but only care you have to take that all the source should be nullified. Same thing you are doing then Vx by Ix. Only thing, if it is a voltage source, kill it, if it is a current source, open it. So, what I just discussed, that is written here. Alternatively, the output resistance can be found by eliminating the input signal source and applying a voltage signal Vx to the output of the amplifier, as shown is next figure. Okay. So, I and Vi, II and Vi should be both 0. This is our objective. Now, can you remember this? Something is known to you? Which one is known to you? This BJT is known to you, right? Which kind of BJT? Common emitter and NPN, right? So, this waveform you know, this is transfer characteristics. This model you know, have you seen this or not? Hybrid parameter, small signal model, this is not done. Okay. So, do not worry. So, this terminal is collector, this terminal base, this terminal emitter. Convention, current is flowing away from base to emitter, right? Arrow is showing like this. So, this should be P, this should be N, this should be N. So, this is a, if it is like this terminal, no, first tell me which terminal? Emitter, wherever the arrow it is emitter, this is base, this is collector. Arrow is coming from this side should be P, this is N, this is, so this should be, do you need to remember now? I hope from now onwards you will be no confusion. So, this is my NPN, this is my PNP, this is my symbol. Now, how many junctions are there? So, do not worry, I am not teaching BJT, I am just continuing my first chapter. Just as we have explained the model of amplifier, we are just continuing that. Okay. I am not entering into BJT, that I will enter in the next class. Okay. So, do not worry. How many operation region are there? 3. Can you tell me? Active, saturation and cutoff. Condition for cutoff, base emitter junction and emitter collector both are in, both the junction is reverse biased. Saturation, both are in forward bias. Active, base emitter forward and collector base reverse. Okay, this is our definitions, why so, and that we will discuss later. So, this is our plot, right. Now, you see I have a transistor. So, just as you said that this is a symbol, right. So, we have a model, equivalent mathematical model for this. So, this is our model. What it is saying, that input side, what is my input side? This is my input side, right, base to emitter. So, there is a resistance, just like you think of your amplifier, input to output, input side there is a resistance. So, this resistance is nothing but R pi. Okay. Let us define this. Now, I have a dependent current source, right, dependent current source. IC is equal to beta IB, that is it. This is my base current, right, this is my base terminal, input side, output side is my collector. So, what is collector output current? IC, relationship between IC and IB, beta IB. So, this dependent current source is having a gain of beta, that is it, and it depends on what? This current, just that. And as we modeled output is current here, this is a current model. So, this output resistance should be in parallel. We are denoting it as R naught. This side, so this is a current amplifier, this is a current model, current amplifier model. This is a input side, you see it is a voltage VBE. So, this is a transconductance model, right, input side is V, output side is current. So, I by V, that is transconductance, this is I by I, that is it, otherwise both are equivalent. So, if this input is VBE, because of this VBE I will get a current of IC. So, how to get a current from a voltage? We have to multiply it with transconductance. Transconductance means what? I by V. So, VB will get cancelled, you will get I, right. So, this is we denote as GM, easy, make it easy, okay, you think it easy, then it will be, you will enjoy it. Do not get confused in what is R pi, I do not know, what is GM, I do not know, you just think of a mathematics, okay. This is my IB, this is a dependent current, output should be IC. So, IB is equal, IB and IC some relationship is there, that relationship is multiply it with a gain. So, this is beta IB. Now, here I have a input is voltage. So, I have a input, this is base, this is emitter. So, terminology says it is VB, okay, VB, input side is VB, output side is what? IC, right, this is a transconductance. Now, this should be give me a current. So, how to get a current from a voltage? I have to multiply it with a transconductance. Similarly, if you want to get a voltage from a current, what you should multiply it with? Resistance, just that. So, it should be inverse of resistance, that is it. And what is this R naught? This is output impedance, you think of that much, the details we will learn later. So, these two model, okay. Now, what we will do? We will add the voltage sources, right, Vs and Rs, done. Output side we will add a load resistance, done, that is it. Now, there is something written as Q, you know what is this? Q point, what is the definition, can you recall? Operating point, okay, you will know a little bit. Okay, now, let us discuss about this different region. So, up to this what region? Saturation region. This flat region is my active region, when the current is 0, that is my cutoff region, right, these three different region. Now, let us come to this circuit. This is what circuit? Which one is grounded? Emitter is grounded. Input is given to which terminal? Base. So, this is my input side and output is taken from collector. So, output and input, which side is common? Emitter is common. Emitter is also in between input side, also in between output side, and it is grounded. So, this is common emitter. You just see that where the input is given to the base, so it is not common base. Where the output is taken, collector, so it is not common collector. What is the remaining terminal that is grounded? Emitter. So, emitter is common. Why common? when we apply a voltage source, right, this will go to this, where the other terminal is going, ground. When you are taking a output voltage, this is V0, where the other terminal is going, ground, and where this ground is connected, so this is common emitter, remember. So, if you understand the concept, then you will never forget. Okay, fine. So, this is a common emitter. What is our load? This is a resistance, right, resistive load. So, this is a resistive load common emitter amplifier. Resistance is a passive element or a active element? Passive element. So, this is a also this is termed as passive load common emitter amplifier. Now, we discussed about the transfer characteristics. Let us discuss this transfer characteristics. Okay, say for example, this input is 0. What will happen to the BJT? This BJT, say this is Q. This Q1 will be on or off? Off. This Q1 will be off. Any current will flow through this? No. So, this voltage will become, think again, no current is flowing through this. So, drop across RC is 0. So, this voltage will be pulled up to VCC. So, you see output, this is my output, VC is your output, right. What is your output? CE. Your V0 is equal to VCE, and when Vi is equal to 0, output is VCC. You see that is happening. Input is 0, output is high. Now, you think that this input is very high, say VCC, very high, transistor is fully on, maximum possible current I have given to the base. What is maximum possible current, possible voltage? VCC, that is given to the base. So, what will happen to the transistor? It will be on. What region that's, but what you can say that it is voltage is maximum, so current should be also maximum level, right. So, if maximum current is flowing through this, so this voltage will go to minimum, right. If no current is flowing through this drop is 0, this voltage goes high. If more current is flowing through this should go in opposite, right. The drops you are subtracting. What is your output? KVL, VCC minus, that is your equation. So, if this goes up, this goes down. If I goes up, this goes down. They are inverse because of this minus sign. So, you see now your input is very high, output is 0, agree, and in between you have to connect them. So, in between you have a something like this, make it simple, just like a digital circuit. What is that? I am giving a 0, I am getting a 1, I am giving a 1, I am getting a 0. What is this? Inverter or NOT gate. So, on a full scale, this is my logic 1, this is my logic 0, right. Transfer characteristic, this is linear or non-linear? Flat. This portion flat, saturated, right, non-linear. Linear what? I told you now y is equal to mx. So, this portion linear or non-linear? Non-linear, saturated. So, if it is saturated, it can behave like a digital circuit, two logic level, logic 1, logic 0. Input is increasing, but I am only interested about the logic, right. Digital circuit, you think of digital circuit. I am only interested about 1 and 0. In between I am not interested. In between this slope I am not interested. So, these two mode it can behave like a digital circuit, inverter. Where I can use it as an amplifier, which region? Active region, you see. You know y is equal to mx, this or this, right? This is my linear region. Why? Because in this region, if my input is changing, my output will also follow. The moment it will cross this, what will happen? It will get clipped. So, let us discuss what regions are they. Input is 0, base emitter it is less than 0.7, it is in which mode? Cut off. So, it is cut off. Input voltage just above 0.5, 0.7, base emitter junction is forward bias or reverse bias? Base voltage is above 0.5, 0.7, forward bias, and when it is forward bias, large current is flowing and this voltage goes to 0 or close to 0. So, VC collector is less voltage than base. Collector base is forward bias or reverse biased? Reverse biased. So, base emitter is forward, collector base is reverse. Which mode? Active. So, linear region, linear means curve is linear, the terminology is opposite in BJT, okay, do not get confused. So, this is active mode. Now, here input is very high, right, input is close to VCC. So, base emitter is forward bias or reverse bias? Forward bias. This voltage goes to this collector base emitter forward. This one is what is happening, saturation. What is the condition? Base emitter forward and collector base also forward. I will just check it. Okay. Next is your load line. Can you recall this load line? See, this is your IC versus VC for several values of IB. Okay. This is say IB0, this is IB1, this is IB2. So, what you are doing? You are changing the base current and the collector current is also changing. You are changing the VC, your collector current is also changing. So, this is your complete plot, right. Now, in this complete plot, where you should bias your transistor, what I told you that this transistor you are giving a voltage, right. You are giving a DC voltage and on top of this DC you are adding a AC voltage, right. This DC voltage you are giving to bias it, right. You want to bias this so that it can behave like an amplifier. So, this is my objective. What is my objective? To make an amplifier which can amplify something. What it is amplifying? Which signal it is amplifying? This signal, AC signal, right. I am giving a small sine wave, I am getting a big sine wave, that is my objective. So, this sine wave, this is a variable, this is a AC current or AC voltage, right. But this DC only for biasing, so that this transistor is in which mode? Active mode, right, because in active mode it is linear, we saw it just before. Now, this to do this, okay, see, to solve this circuit, that what is my current and what is my exact solution to this equation, okay. I have two current flowing through this. See, one is current flowing through the resistance and one is current flowing through the BJT, right. If a current flow through a resistance, what is the equation? I is equal to V by R. My equation for this current flowing through this resistance is V by R, and when V means this voltage drop, right, VCC minus V0 by R, right. When this drop is minimum, when this drop is minimum, your current is minimum, and when this drop is maximum, your current is maximum. Agree? So, this is Vc. When this Vc is 0, what is the drop? Maximum Vcc minus 0. So, when Vc is 0, my drop across resistance is maximum. Agree? Total Vcc. You just make this a equation, I is equal to Vcc minus Vce by R. So, if Vc is equal to 0, my current will be maximum. So, this point. If my Vc is equal to Vcc, Vcc minus Vcc, what is my current? 0. So, I get a equation for, this is for which current? This is for current flowing through the resistance, and this plot is for what? Current flowing through this BJT. Now, this is variable because I do not know which point is suitable for me. So, I am plotting all the possible current. Now, where this same current will flow through this, right? So, whatever I that is flowing through the resistance, that should also flow through the which terminal? Collector terminal. This current, there is no path, right? Whatever current that is coming from the resistance, that should go through the BJT. So, from this graph, wherever they have cut, this is my solution, right? Same current should flow through the BJT also. So, this point, this could be my solution, here it has cut, this could be my solution, here it has cut, this could be my solution, this could be my solution, this could be my solution, right? Same current is should flow. So, whatever is my IR, that should be my IC, right? What is the graph for IR? This line, and what is my IC? This line. So, this could be my, they are same here, right? This all other point it is not feasible. So, this is called graphical solution. I can give you equation, right? You can calculate the I, but here what I am doing? I am plotting the graph, from there I am seeing the where they have intersect, that is also my solution. Okay. So, from mathematical equation you will arrive to this same point, right. So, you will be calculating, say I is equal to this or this or this, right. So, so many possibilities are there. Now, what you have to find out, that what is the best solution for me, that is your Q point. This could be your Q point, this could be your Q point, this could be your Q point. So, which one should you choose? It is my question to you. Which one should you choose as a DC value, so that you can amplify? Can you tell me? Should it be at the corner or should it be at the middle? It should be at the middle. Why? This is something like this, right? If I am at the middle, I can go below and above also, right? So, if my input is changing like this, my output will change like this, but this is my DC value, this is my DC value. So, I have a roaming position, but if I choose my Q point like this, at this position, upper side very little position is left, lower side I have full position. So, this is not suitable, output is not amplified, this is distorted. If I choose this as my Q point, what will happen? Lower side I do not have room, upper side I have full room. I have to amplify it, right? I have to amplify for a sine wave. Sine wave I have both upper half and lower half. So, where should be my Q point be? Middle. How we are choosing this Q point? We are solving the transistor plots, we are solving the current through the resistance, wherever they are crossing, that is my possible solution. From these solutions, we will see that which one is coming in the middle. That voltage and that current should be my DC value. So, if you have any confusion, do not worry, we will again discuss this, okay. Because this is a beginning, I am just building up the basic, okay. So, we will be again coming to this, and about this saturation region, I will discuss this in next class, okay. So, if this is your Q point and this region you see, this is linear region or you are in still in active region, here you can act as an amplifier, but you have to remember, to act as an amplifier your input signal should be small. Why it should be small? You see this signal, you see it is so small. It is which signal? VBE. You see this input you are giving in the base emitter, VBE, right, VAC, that is actually your VBE. This is small VBE, means AC signal, and this should be small. Why it should be small? Otherwise it will get out of active region. You see this active region is so narrow. So, if you get out of this active region, what will happen? It will be clipped at the output. Why clipped? Because this is not linear, this is saturation. So, if this is small and if it stays within active mode, the output will be amplified. Actually, why it is amplified? Because in active mode your IC is amplified, right. So, if IC is amplified, ICRC will be also amplified, but because of this minus sign it is coming in what? Opposite phase, minus sign, 180 degree out of phase. What we just saw, this is behaving like a inverter, means if input is high, output should be low. So, if input is increasing, output is decreasing. In which region? This region. Other two region it will behave like a flat, right, high and low. So, that is selecting the Q point. So, where we should select? At the middle point. So, let us stop here and we will be continuing from frequency response of amplifier in next class. Okay.